so how all these things started? Yeah, at about maybe 93, I suggested homological mirror symmetry. And homological mirror symmetry says that you have, let's say, symplectic manifold with first chain class equal to 0. You get mirror dual complex algebraic manifold. In fact, depending on small parameter, something like this, on some form power series degenerating, and then Fukaya category of the things, which is naturally T goes to area of disks. This participate how in Fukaya categories should be equivalent to boundary derived category of coherent shifts on this X dual. Okay, so it was a nice formulation, but it was on form power series, and we expected it's convergent and go beyond form power series to actual manifolds. Yeah, that was the idea, and from which we can draw a lot of consequences. And when it started, it was a bit too early for mathematics, and also a bit too early for physics. Because what is this category? Yeah, one can say you have topological field theory, have some boundary conditions, but then later comes the D-branes. D-branes exist in the following context. You have n equal to 2 superconformal field theory in two-dimensional. It's not string theory, just conformal field theory. And then you have two topological twists, A-B topological twists. So you get, from this you can try to build categories, and then kind of two categories. But D-branes are is a extension of your conformal field theory as a unitary theory to the boundary and preserving half of mirror supersymmetry. Unitary extension to boundary. Boundary theory with half of supersymmetry. So it's some kind of objects, and then Mike started to think, just compare things coming from physics and math, and realize that there's some kind of little discrepancy. When mathematicians talk about this triangulated categories, whatever, the home spaces are graded by integers. Home in this TQFTs, whatever, TQFTs, graded by integers. And between D-branes, you can consider kind of like interfaces. D-branes, it's not by integers, it's by some real numbers. But it's almost by integers, it contains some shift, oops, there's another blackboard, shift by, integer shifted by some real number. Oh, sorry. And this real number, yeah, so that's the whole story came from this. Yeah, so this real number, kind of a real life example, one can imagine like you have, let's say, in large volume limit, you get two special Lagrangians. You get two special Lagrangian manifold. So what does it mean? X will be Calabi-Yau with Calabiometric. You have the scalar form, and you get holomorphic volume form. N will be dimension, not necessarily 3, because we don't do string theory. You get two special Lagrangians. The special Lagrangians means that argument of omega is equal to some angle mod, let's say pi, and argument of omega and 0 restricted to L2 will be another angle mod pi. Then this constant here will be θ2 minus θ1 divided by pi. Yeah. So that was little discrepancy, and then he formulated rules. What happens with D-branes when you start to vary kind of like Keller parameter in your theory? Don't change category, but change kind of Keller parameters. What happens with D-branes when you start to vary some kind of other parameters, like here complex structure? Preserving categories. So they appear, disappear, there's some kind of instability picture, and then Tom Bridgeland translated to notion of stability structure. Yeah, so that's it's at the end of the day, it's kind of this shift by real numbers. It's equivalent language, but it's mathematicians never adopted it. Yeah, so they still keep grading by integers. Yeah, that's actually, this grading really makes sense only for stable objects. For non-stable objects, one cannot make sense of it. Yeah, so I'll just recall you. Recall it's really for mathematicians mostly what is stability structure. Yeah, you have some triangulated category. Yeah, so it's something with homes are graded by integers, and also have shifts, which makes no sense for D-branes. What does mean the shift? It makes D-branes is something that's logic. You can forget about shifts. You get shifts, like shift complexes by some integer. And then you get, there is something called K group of category, which is usually something absolutely huge and humongous. You consider all exact sequences, which is called maybe exact triangles. You get consider all exact sequences and say that symbol associated to F is equal to symbol associated to E plus symbol associated to G. You generate some huge Grothendieck group, which is something huge. And then you map it to complex numbers. But in order to map to complex numbers, maybe called something like Z algebraic, because consider algebraic case theory. Yeah, so these groups we can't really understand it, but you can map it to something reasonable by some kind of finite number of topological charges. In physics, topological charges map to some lattice of finite rank, and then actually go through this guy. And what happens, for example, in real life, like in Fukaya category, if you have Lagrangian manifold, you can associate to it. It could have some local system, but you just associate a class of L, maybe multiplied by rank of local system in middle homology, maybe up to torsion. Yeah, so you get finitely many integer numbers if you choose a basis, and the integral is calculated through this data, not through this abstract story from a category. Yeah, so what happens then for each real number in R, you have just collection of objects. What's called full subcategory. Just keep track really about objects. Homomorphisms will be the same. And with the property that C of theta plus pi will be C of theta, you apply shift by 1. And then there is another property that for any object there exists unique sequence of morphisms, such if consider quotient and triangulated category for each morphism, we can make a kind of like interpret as inclusion, take a quotient. It's denoted by con in this formalism of triangulated category, is semi-stable with certain slope sigma I, and sigma 1 is bigger than sigma k. I claim that there exists unique filtration, and this one can unwind, get this Bridgeland axiomatics, you get plenty of abelian categories, mathematicians are very happy, you get huge amount of algebraic things. And there was something to add here. It's what we called with Young support property. I say the following way. So it's continuous family of convex cone, of strict convex cone, cone depending on direction. Direction will be now in R mod 2 pi z. And cone belongs to what? You consider you have this map, central charge from Zn to Z. You consider extend to real numbers, and consider pullback of the ray. In complex numbers. Yeah, so I should draw the picture. Oh, yes, really. Sir? Cone theta, yeah. It's not category theta, it's cone theta. Maybe theta mod 2 pi z. Yeah. So this, yeah, like imagine that, for example, the rank of my lattice is 3. I get some 3 z cube maps to C. So how to write it? We draw a plane. We consider some 3-dimensional space. And then a 3-dimensional space, we get 0, goes to 0. And then we get some integer points, yeah? And this support property said that for each direction, I have kind of like maybe straight cone, but maybe some, you get some picture like this, which if you intersect with, let's say, with some ray, you get some angle sector in a half plane. If you rotate, you get another half sector. And these things actually can change size. Yeah, so you get this continuous family of convex things, which can sometimes disappear. In some domains, you get empty cone. Yeah. So it's a pretty complicated picture. And what physics suggests that you should have not only the stability structure, but this family of cones as well. And the family of cones will support it will call support property if you have any object in C theta, this non-zero semi-stable object, then we can consider kind of like Chern class, kind of like then Chern class of E, which belongs to lattice. It belongs actually to this cone. Yeah, that's a property. So you don't have objects which stay whose central charge stays too close to the kernel of Z. This comes from kind of from geometry. Yeah, for example, you can try to think about the special Lagrangian manifolds, and you see that kind of immediately you can write bounds. Let me tell you just kind of one important example. Let's suppose X is a torus. and kind of translation invariants, invariant omega. I have this just flat torus. This category, which you can see the Fukaya category on the things, it's kind of Lagrangian manifolds, is, we don't know what is it, but if symplectic form has kind of irrational coefficients, general coefficients, then there will be no Lagrangian manifold whatsoever, at least special Lagrangian manifolds whatsoever, because if you have homology class, it should be killed by, it will be integer class and killed by form, but if everything is irrational, you cannot find such integer homology class. Yeah, so this K0 is of kind of algebraic K0 of the category is very unstable. So it's in generic point it's 0, and then it's some very dense set. It's kind of became larger and larger, and then it will be kind of stupid to put support property just on kind of accidental fact how many objects it happens. But how to write these cones? This lattice, which you intersect, the n, will be something like z to it will be a rank of primitive homology H primitive n homology, sorry, n primitive homology what I'm writing about. Okay, yeah. So this, maybe before going to lattice, what I should consider. Yeah, maybe consider all homology of your manifold. Of my torus. And when you get symplectic form, we get a map to complex numbers. Yeah, so it's something of very huge size. And now, how to get these cones? If you fix a direction, if you fix theta, consider part of Lagrangian Grassmannian of just n-dimensional Lagrangian Grassmannian of n-dimensional subspace of R to n. Here we get fix a codimension 1 subspace Lagrangian Grassmannian with slope theta. It will be possible tangent space to your Lagrangian manifold at any point, if it's special Lagrangian. And then we can make convex hull of it. So we take convex hull and make a cone of it. So we get kind of cone over this guy. Get some kind of complicated cone depending on theta, and this will be something which geometrically bounds you all possible special Lagrangians. It doesn't matter whether special Lagrangians exist or not. If you have this non-integral homology class, you get automatically a family of cones. And this behaves kind of nice continuous way, and it's not really encoded in Bridgeland axiomatics, but that's what naturally comes from the picture. Okay.
Maxim, but what are the branes for this irrational torus?
Oh, there's no branes.
There are no branes.
Yeah, okay, but still.
If I do wrap a physical brane, it will stabilize somewhere.
No. No, there will be no Lagrangian submanifolds.
I understand. So it will what will break supersymmetry?
No, there's no brane. There's nothing. There's no branes to talk about at all. Yeah. Its category is nothing.
So your category is empty.
Empty, yeah. Zero objects, maybe. It's Gober will say, yeah, okay. Yeah.
Because you break supersymmetry.
No, you cannot find charges which are.
No, so there will be non-supersymmetric stable states.
Right.
I
don't think there will be anything here.
But what can happen to the brane? I mean, that can.
Yeah, I think everything.
Oh, no. There is a its homology is conserved charge.
No, the brane it will be not.
Try to minimize energy. We should probably be search for the best approximation to irrational periods.
No. I don't think there's anything here.
That's it.
We're saying there's some minimal volume. some minimal volume manifold.
Some minimal volume.
It will be not supersymmetric. Yeah, no. No, for these categories, this everything breaks down. There's nothing to do.
But if I slightly change omega, so make it rational, then suddenly they appear.
Yes. No, omega. Yeah, then will appear. Yeah, that's the point. Yeah. Yeah. So it's so there's definitely no categories to speak about in general story. Yeah. So these things actually. I said you can Fukaya categories. And
sorry, what about quasitropic branes? So if n is even, so 2n is divisible by 4, then sometimes we have branes which are not Lagrangian.
Yeah, I will also talk about it. Yeah, I consider in kind of Fukaya category limit. I don't consider only Lagrangian thing at the moment. I will go back to quasitropic branes later. Yeah. So here one can try to formulate mathematically what is going on. And so in general, if you have, let's say, Calabi-Yau variety, you want to have the special Lagrangians, and something like this. But and then if you then this series Fukaya category started, people spoke about smooth Lagrangians, and special Lagrangians are not necessarily smooth, especially in high dimensions. You can expect some kind of singularities. Yeah, so it should allow singular Lagrangians, and then it leads to some kind of general project what to do in Fukaya category in theory. For Fukaya category in general, it leads to some kind of project which I started, but it's not. It's still it's very well under development. If you have kind of singular Lagrangian subset, not a submanifold, some kind of L singular sitting in your guy, like on plane, you can have actually in R2 you can have just graph with some singularity. Then one should have kind of two steps. One should associate local Fukaya category of a very small neighborhood of this guy, and because it's very small, there's really no holomorphic disk around. And this thinks it should be something over integers. And like if L is singular, smooth variety, it will be local systems. You can see, and you have algebra like group ring of fundamental group with integer coefficients and kind of finite dimensional modules. It's maybe modules, finite dimensional modules of algebras over integers, I would say. But for this picture, you consider like exact triangles. You get two objects, some morphism, and cone of morphisms. You get this. Exact triangles nicely represented for this guy. It's some kind of combinatorial notion. There's no coefficients here. And then holomorphic disks in X with boundary on L on this give some kind of small deformation of this category. You get formal deformation. And there would to be the definition of Fukaya category will be kind of union or inductive limit of all possible singular subvarieties of this deformed this Fukaya local of the cell singular. If you have one Lagrangian variety, another Lagrangian variety, take their union, it will be still singular guy, so one can kind of formally make its inductive limit. Yeah, you get some category over, form power series with maybe non-negative powers of R because you have actual disks, and then invert T, and you get actual Fukaya category. You consider Laurent series. Yeah, so that's a picture, and so the conjecture is if we have now this holomorphic volume form, which is not necessarily Calabi-Yau metric, so we should can have Calabi-Yau volume form, but some Kähler form not necessarily satisfying Ricci flatness condition. Then special Lagrangians. We consider deformed Fukaya category of special Lagrangians. This will be your category C theta. Will be Fukaya category of X theta. It will be all semi-stable objects. You consider anything in singular guy, add formal power series. It doesn't destroy stability in this formal sense. So you get this description what are semi-stable objects and how to prove that anything expands in some canonically in some exact sequence. You should make some kind of flaw. If you get general, not singular Lagrangian guy L, you start to deform it at least in smooth point. Start to move with certain speed, and speed is a section of a cotangent bundle, because normal bundle is cotangent. It will be graph of, it will be just one form, closed one form on L, maybe minus singularities, equal to differential of argument of omega n 0 restricted to L. Yeah, so it's one can define some kind of like mean curvature flaw for this Lagrangians, and then one can make hand-waving arguments to show that it's eventually it's the limit you should get semi-stable pieces, and they will be ordered in this.
Yeah. Can I ask, because it seems like there are two ideas here, as so far as I understand. So one was to say we don't have to take the omega to be the let's say the quasi-algebra.
Yes.
A generic omega. And then we can make this kind of local construction.
Yes. Yeah, this local construction has nothing to do with stability. It, even Calabi-Yau has nothing to do. Yeah, precise definition of Fukaya category. But next story is that for this volume, holomorphic volume form should not necessarily compatible with symplectic form in
But you say Lagrangians really still would be.
Lagrangians is for symplectic form, yeah.
But it wouldn't matter what the omega is. So you would still get the same set of stable.
Yes, you can describe in different omegas and get the different description of stable categories, and you can have freedom of choice, kind of, yeah. But in fact, there is something more here. There was something which bothered many people from the very beginning. From physics, you get some family of categories with stability coming from this conformal field series, and stabilities form some central charges, some maps from this lattice to C, and okay, you get some certain families. But Bridgeland proof kind of easy theorem. If you have stability structure, you can deform the central charge in open cone, in open neighborhood, and you get much larger family. So dimension of family will be dimension of cohomology, which is much larger than dimension of model space. So have, like mathematically, have more stabilities than we have coming from physics. And how to deal with this story? For example, here says omega n 0 form. In fact, one can even generalize it further. One can generalize omega n 0 form just to n form with complex coefficients. Maybe which is closed, or primitive part is closed. And such that if you restrict omega to the tangent space to any Lagrangian, you get non-zero for any Lagrangian subspace pointwise. So it's kind of open conditional space of n linear forms on two n-dimensional space. It's a very interesting story. Here goes on. This my former student Fabian Hayden wrote a paper. So there's kind of really great things in linear algebra goes here in this situation. So one can get automatically one can relax conditions enormously. So not even complex manifold. Yeah. So one can do this things in a very great generality. hook. Then, because several years ago, I came to huge generalization, which is barely started, Fukaya categories with coefficients. What's it all about? Again, let's think first about Calabi varieties, and suppose have a Calabi variety, and then imagine that it's project to some smaller space or a Kähler manifold of smaller dimension. Usually it's kind of like Fano. Yeah, I like imagine like K3 maps to P1 and fibers are elliptic curves. Singular at some point. You get some projection. And so I have this picture, you get, let's speak about volume form, usual volume form on X. But now I want to make, for Kähler structure, I have omega y. I can choose Kähler form on X and Y. On X maybe it's Calabi-geometric, but on Y it's not. And then add something like, write something like this. It I make very large, take pullback of Kähler form here. So I get Kähler metric such that fibers are small relative to the base. Fibers are small relative to the base. And now, if we're interested, what are special Lagrangians? By the way, I don't want to multiply by epsilon because all this convergence we expect when symplectic form sufficiently large. So I should go in it at infinity, but with different kind of rated horizontal and vertical direction. So if I'm interested in special Lagrangian varieties in X, and then I try to think what is it, and this will be the following. Locally it's like product with fiber with a flat space. And kind of generically, except some points, it will be really product of special Lagrangian in the fiber with some straight subvariety in a base. Straight kind of affine subspace, affine special Lagrangian in Y. Or if you go to the limit, it will be essentially the following things. On the base, you get on each fiber you get special Lagrangians, and then the things on the base will be special Lagrangians with certain form which depends on choice of special Lagrangians on the fiber. If you get kind of Ly sitting in minus 1y special Lagrangian, then I can associate a form, locally form on M form. Yeah, it's something of dimension n minus m. You can see, and we associate M form, complex M form on the base, near y. by integrating omega n 0 of this guy, you get a remaining holomorphic volume form on the base. And then things on the base will be special Lagrangian with respect to this thing which depends only on the homological class of this guy. So what we see here, yeah, speak about first about stability, but
hey, what do you mean by affine? If there is no affine structure.
It's not affine structure, but in kind of if you can rescale metric and look on kind of distance one, it looks like essentially like a flat space. But then if yeah, so and what here happens? You see that you get kind of like a local system, or maybe outside of some singularities, outside discriminant locus of projection of categories, Calabi-Yau of categories, which will be Fukaya category of the fiber, when we restrict this guy of Fukaya categories with central charge coming from these categories and maybe to some group like middle homology, yeah, Hn minus m fiber of torsion, and maps not to C but one-dimensional complex vector space. One-dimensional complex space, which is H wedge M of cotangent bundle holomorphic kind of 0, 1, 1, 0 star of Y, which will be isomorphic to C but not canonically. It's yeah. So one can formulate the notion of central the stability when you have central charge not values on C but just a one-dimensional space as well. And then what we see that special Lagrangians we can describe as the following way. We get locally we get some singular Lagrangian subset. Then at each point we choose stable object in your fiber category, and the base should be special Lagrangian with this volume element coming from this central charge. Yeah, so that's a beautiful picture. But now you see that you don't have to, and something happens in singular fibers. So I think Misha Kapranov talked a lot about perverse shift of categories. There's some interesting category theory goes around singularities. But just beside, without this, you get interesting notion. And you see that you don't need these categories which you come from the fiber to be coming from physics or the symplectic geometry to anything. You should have very abstract story. Get abstract local system of categories with stability, and then you get stability on this volume elements, and then you should get this notion of special stable object on the total category. And particularly, forget about stability, you get certain construction. You should get, for this local system of categories, this could be any coefficients, like mod 2, whatever, you should get Fukaya category with this coefficient. So it will be very general kind of like shift category future of this Fukaya world, when you can put these constructible shifts with singularities of codimension 2, 4, and so on symplectic manifolds. And in this way, one can really get a lot of things. And if one believes this picture, then by induction, one can construct stability on like abelian category for abelian shift of abelian variety, depending on many parameters which decay with different speeds, like iterated Laurent series. Yeah, there's a very interesting story when, for example, when the base is R2, and you get kind of constant family. So it means that for any category with stability structure, one can construct a new category who will be represented by some kind of like pictures like this, it will be straight lines, and on each straight line you put object of your fiber category and put exact triangle condition here. Yes, this is already very non-trivial, and one can formulate this flaw already in case of R2, and I tried to work for several years with my colleagues and collaborators. It's kind of very non-trivial question involving just abstract stability structures is in general category and some kind of a little bit of analysis. Yeah, because then you should make kind of flow. You start with some not straight line and then move. And already in two-dimensional examples, it's a very non-trivial story if you put coefficients. Yeah. Yeah, so that's one big generalization. And again, one can replace holomorphic form by this very more soft open condition forms which are just positive on Lagrangian subspaces. Yeah, it's all this was all this is about Fukaya categories. Yeah, let's just say I'll return back to our usual Fukaya categories. Don't forget about coefficients. And Fukaya categories are over these non-Archimedean fields. Maybe it's rational coefficients. Yeah, so they're on over non-Archimedean fields. And they're really, technically, it's something very hard to construct Fukaya categories with all these definitions of disks and transversality. It's a bit of nightmare. But one can use it as a kind of like black box, kind of application of these ideas, but not of mirror symmetry. You don't have to prove mirror symmetry. Suppose now have variety, algebraic variety over non-Archimedean field. Which is something which I assume to be a mirror dual to Fukaya category of symplectic manifold. If you fiber your symplectic manifold over some real base, you take real integrable system. And here on mirror side, algebraic variety of non-Archimedean field, it also has kind of SYZ fibration. There's notion of non-Archimedean SYZ fibration, which is not unique. You map to something, some real space of dimension n. And here it's algebraic dimension of axis n. Such that it has some kind of, again, discriminant of codimension 2. And outside of discriminant, on B minus discriminant, you have integer affine structure. How it locally looks like you imagine like torus. You consider punctured line minus 0. And if you have coordinates z1, zn, which belongs to your field, which could be form power series, you map to, by logarithm of norm, to Rn, to log of z1, log of norm of zn. Yeah, so on an Archimedean field, to get a map, a log of norm, which goes from k star to real numbers. You just apply it. Okay? So you get a map, and the fiber is some kind of like non-Archimedean tori. But automatically, these things, you have change of coordinates like SL and Z acting here, JL and Z, so to get integer affine structure on the base. And when you get integer affine structure, you kind of like completely formally construct a torus bundle. You consider cotangent space of the base space divided by integer part. And do something with singularity, you get formally symplectic manifold, real symplectic manifold. But it's completely formal construction. And mirror symmetry would be that Fukaya category of this guy equal to this category of these things. But now one can use these ideas to make a suggestion. What will be stable object for this coherent shifts here. See the stable objects in dB of coherent shift on X. Yeah, kind of a posteriori we know the answer. It should be some singular Lagrangian guy here. We draw the singular Lagrangian guy in this base, and then it projects to the base. It's not really equal number of folds. Somewhere it could be 1 fold, somewhere it will be 3 folds. And the picture, it will be the base you can cover by open pieces. And here it says that it's a vector, it's a line bundle. Or here it's 3 line bundles and some maps which you cannot see in the limit. And here it's 1. Yeah, so you describe your stable object not as a 1 vector bundle, because people know that it couldn't be 1 vector bundle, it's complex, but what size of complex? And size is changed in different domains of the base you describe as complexes of vector bundles of different ranks. He'll be 1-dimensional, he'll be 3-dimensional, and how to see what is a special Lagrangian. You consider this object of coherent category with metric. Yeah, that's very general story for any things of a non-archimedean field. One can say this object with metric essentially can take model and kind of make approximation, take a metric. And if your Lagrangian manifold is graph of df, then you get, say this line bundles will be a trivial bundle, and norm of 1 at some point y will be exponent of f of y. Of point of x will be exponent of point of y. Yeah, so just formally declare for trivial bundle on trivial sections, the norm will be exponent of this function. Why it sits in a torus? Because on trivial line bundle can multiply by power of monomial. And multiply power of monomial, you add to your function linear functions with integer coefficients, but graph of differential will stay the same if you mod out by integers. And then one can formulate abstractly how object with metric gives a Lagrangian guy. So you have object with metric, and what is what will be corresponding Lagrangian subset? It's from some abstract shift theory. If you have kind of object with metric, then on base multiply by real numbers with coordinate lambda, I consider like sections of E, roughly speaking, of E, whose norm is logarithm of norm is less than lambda. I get some kind of sub-object depending on lambda and on point on B, near point B. I get certain sheaf, some horrible sheaf, on product of base with real numbers, and then you take something called singular support in terms of the theory of Kashivara and Shapira. You get singular support, which sits in a cotangent bundle, and it will be conical in 2 sense. It's in cotangent bundle also in this direction. And then if you get non-conical subvariety in cotangent bundle by reduction by expansion, you get non-conical in cotangent bundle, and then this non-conical cotangent bundle will be something like this. If you consider like B is R, then you consider this one bundle, you take universal cover, get cotangent bundle, and the single support will be infinitely many copies on the universal cover of this guy. You pull it down to the torus, and you get the single subspace. And now you want this guy to be special Lagrangians, maybe with respect to this crazy n forms. Yeah, so it's now a question for analysis. Yeah. So the suggestion is people working like in periodic numbers can construct stability structure, but they have to solve some very non-trivial PD just to get a concrete description. Yeah, that's one story, and maybe just last very short remark I want to say. I just draw some numbers. What are these numbers? Yeah. This number is actually Catalan number with index n plus 1. And it has the following meaning. It's the maximal possible rank of algebraic K-series modulus and numerical equivalence from what you see in the charge lattice of Fukaya category, and the variety which I consider will be flat torus. Over Novikov ring. Yeah, we consider Fukaya categories over non-archimedean guys. Then the maximal possible rank is of this thing, it's H2, and it's achieved, for example, if you take torus and raise to power n. Get copy of the same torus to some power, you get this maximal rank. It's very symmetric. It have some symplectic group acting here. And this category is equivalent to, Fukaya category is equivalent to Fukaya category of generic elliptic curve to power n. And no, category of coherent sheaves. And then the rank of K group, where we see numerically, it will be exactly this guy. And these are represented by Lagrangian subtori and things like this. Now, what is this? This is a more interesting story. It's maximal possible rank of, again, algebraic K-series of, let's say, Fukaya category over complex numbers, whatever it means, or dB of coherent sheaf of abelian variety. It's actually achieved for many abelian varieties. You can take either abelian variety with complex multiplication, some very big symmetry, or you take elliptic curve with complex multiplication, something like C mod Z plus IZ, very special one, and take its sense power. Then we'd have more classes. The categories will be much larger, and the rank of K group will be larger number. What does it correspond to in Fukaya world? In Fukaya world, it corresponds if you kind of believe that there are actual categories, and then not on form power series, then it should be for some special values of omega and b, you should have quasitropic branes. And this to n over n, it's not what you think, kind of. To n choose n, it's not more or less the rank of middle homology of the torus. Of course, it's equal, but yeah, but it has a different meaning. I think it's for this kind of very symmetric. I think it will be rank. It is equal to rank of what? I consider h n primitive of the torus plus hn plus 2 primitive plus hn plus 4 primitive, and so on. This is again the same number, but it represents homological classes of Lagrangian submanifolds, Lagrangians plus some one complex dimension, two complex dimensions, so on. This is quasitropic branes by Kapustin and Orlov. Yeah. So it's get quasitropic branes. The category which we have here, one can describe some kind of like Narayan space. If you go back to space of series, if you go back to conformal field series description, you do the following. You consider like CFT sigma modulus varies in a torus of dimension 2n. And this usual Narayan modulus space is like this, because dimensions already 2n. You get something like this. It's usual modulus space of Narayan modules. Now, if you want to go to supersymmetric one, you go to un cross un, yeah? It will be Narayan modules is n equal to supersymmetry. And this is kind of nice Hausdorff space, and it maps to something a bit crazy, very non-Hausdorff. You divide by UNN. Which is complex non-Hausdorff manifold. It's complex non-Hausdorff manifold, and this parameterizes some categories from which K-theory can go up and down. It should parameterize the categories, and what you choose the fibers, you choose the stability on this category. But this quotient is kind of like really ergodic, everywhere dense.
Is it also some kind of Lagrangian Grassmannian?
Yeah, it's isotropic Grassmannian, maybe isotropic Grassmannian, yeah. You can see the complexification isotropic Grassmannian, some open part and divide by group, but the action is kind of really ergodic. And so it will be categories, and the fibers, choice of fiber, it will be category plus stability, coming from physics. And then from this picture, I have no real time to take, I predicted what are cones. What will be convex cones will be cones over SUN instead of Grassmannians. One can, some spinor representation, one can make a kind of natural guess what will be the stability with respect to cones. Okay, that's all nice. That's all what we get to in physics from tori. That's kind of very large thing. But what is the last number? It's going really beyond the physics. Yeah, this was what was called, in terms of algebraic geometry, to consider coherent shifts on power of elliptic curve with complex multiplication. Here we get these numbers. There is elliptic curve on a finite field with p-square element. It's called supersingular curve. And if you consider derived category of coherent shift, it's just unique object. There's only one object. But if you raise to nth power and consider rank of k0, modular numerical equivalence, you get exactly this larger number. All even homology will be algebraic cycles. And for these things, again, using a spinor representation, one can guess what is stability conditions, what are cones. But for this, we should really go to kind of physics and finite characteristic, I suppose. Okay, thank you.
So there is something which happens in physics which might sounds like related to your story with Fukaya coefficient. So
yeah.
If you do take your torus, which is with irrational omega,
yeah.
and do wrap a D-brane,
yeah.
but also you have space-time, our space-time.
Yeah.
So that D-brane will become like a massive particle in
yeah.
space-time. It's a black hole.
Yeah.
So what it does, it actually forces the moduli of your torus change.
Yeah.
So you measure at infinity, it's one thing, but as you approach the horizon, it will be actually different. It will be such that omega will become rational.
Yeah.
And so, if possible, so it's called attractor mechanism.
Yeah, yeah.
Sometimes it's flow, so it's kind of some kind of flow on the kind of moduli. Sometimes it splits.
Yeah.
And that starts looking like what you draw here.
Yeah.
So it's probably minimum. So it's probably a supersymmetric cycle, but not in a single Calabi-Yau, but in a family of Calabi-Yau's fiber.
Yeah.
But it also suggests that non-commutative tori, but that's not the question I wanted to ask. So a point in all this that I always wanted to know, kind of the general picture, is that you would think there would be some sort of infinite dimensional gauge group and moment map underlying it all.
Yeah.
And so in physics you could try to see this thing in string field theory, but that's very complicated. And then here, I guess what I see of it in your talk is these flows, but again, for the original.
Yeah, we can make some
For usual special
JT,
function,
no.
they become very singular, and it's hard also to fully understand that. But I wonder if you have any picture, or can we identify that infinite dimensional group?
I don't know. Yeah.
Anywhere?
Yeah, there are analogs of this flow, like for presentation of quivers. Really funny formals. I don't want to bother you, but yeah, yeah, one can do similar things. Like for quivers, also one can see this stabilization coming from some flow, which is some new things which we wrote down with Haydn and Katsarkov. Yeah.
So there's a different flow.
Yeah, there is some different flow. I can maybe tell you just one word. What is this flow? Like for representation of a quiver, yeah? You get a quiver, something like this, yeah? You get some vertices, and you get numbers with imaginary part bigger than 0 for each vertex. Then it gives a stability on usual representation. Now consider metric on a quiver is collection of Hermitian forms on things. And now you write the flow something like this. It should be some self-adjoint operator. And self-adjoint operator is argument of some normal operator. For normal, you have, because I have orthogonal eigenvalues, you can apply any function. Normal operator will be the following. It will be sum over ZV projection to this space EV. It's not self-adjoint because you have a real imaginary part. Plus sum over all arrows of alpha, and we take commutative which will be self-adjoint. So you get some normal operators. These things commute, and real imaginary part commute, and you take normal part, you take this flow, and then this flow start to expand your metric with different speed, and by this different speed you get flags, and you get exactly stability decomposition of general representation. Yeah, so it's not JIT, it's something else, and there's some relation JIT, but it's pretty complicated story here.
Maybe
Other questions? Go ahead.
So one thing about Bridgeland stability is that they form some nice complex manifold.
Yes, domain in vector space, yeah.
Yeah, do you expect this notion of stability as being some collection of cones to also form some kind of family or some nice
continuous family? For this forms you just have some upper semi-continuity with different parameter. Yes, it's the total things should be closed subset, I suppose.
I see.
All right. Looks like
Okay.